Hi, everyone. So we reviewed the standard normal or Z distribution. Z-scores are used more generally, but when we talk about the Z distribution, we're referring to the standard normal. Now, we're going to talk now about the T distributions, plural, because there are many of these, infinitely many of these. The T distributions are also called students' T distributions. Actually, there's a good history to the T distributions. Basically, they were invented and studied by a worker at a brewery in Ireland, and because of the rules at the brewery, he had to publish under the pseudonym Student. So this comes from the work of a brewery worker, although hopefully not while he was drunk. Anyway, these T distributions are similar to the standard normal Z. For example, these T distributions are all bell-shaped, but notice I'm drawing these a bit differently. Well, like the Z distribution, they're continuous. So we have this continuous density curve. We're not talking about bars like for a binomial. A T random variable can take on any real number. The density curve is bell-shaped. The total area under the curve is 1. So far, it's basically like the Z. The mean is 0, again, like for the Z distribution. And again, we have symmetry. So all of these characteristics for the T distributions are the same as for the Z distribution. Nothing is different so far. But now, and also this too. I could add this too. The tails fall off rapidly. I guess I listed the similarities first. These are all similarities, right? The tails of the curve fall off rapidly. Okay, which means that you cannot have too much too far out. You're not going to have too much further than 3 or 4 standard deviations away from the mean. So these are all similarities between the T distributions and the Z. But what are some differences? Well, as I said, there's only one Z distribution. Yes, it can be applied to infinitely many normal distributions, but there's only one standard normal Z distribution. But there are infinitely many T distributions. We don't have a standard T distribution, although we do have a generic bell shape. Now, that's one reason why whenever I talked about bell curves before, I was a little nervous because there are different kinds of bell curves. They're not all normal, like the standard normal. The T distributions also had bell-shaped density curves. So not all bell curves imply normal distributions. Okay, here we have T distributions, and we have infinitely many of them. Now, back with the Z distribution, the standard deviation was 1 unit. For a T distribution, the mean is 0, but the standard deviation sigma is greater than 1. And the tails, by the way, although they do fall off rapidly, they don't fall off as rapidly as for the Z. So for example, for a T distribution, you're going to have more stuff, more probability mass, more than 2 standard deviations away from the mean, more so than for the standard normal Z. So in a way, this represents greater uncertainty. There's greater variability out here in the tails. I should put arrows out here. The tails are thicker. The tails are thicker. Things are more spread out, representing greater overall uncertainty. Now, again, there are infinitely many T distributions, and they're indexed by the number of degrees of freedom. So we have a T distribution on 1 degree of freedom, 2 degrees of freedom, 3 degrees of freedom, and so forth. If you give me a positive integer n, there's a T distribution with that number of degrees of freedom, or df. There's a T distribution on 1,000,000 degrees of freedom. And by the way, that kind of a distribution will really resemble a Z. If the number of degrees of freedom, if the number of df is large, then a t distribution can be closely approximated by a z distribution. I'll discuss that in a moment. But anyway, we have infinitely many t distributions corresponding to 1 degree of freedom, 2 degrees of freedom, and so forth. So in tables, you see rows for 1 degree of freedom, 2 degrees of freedom, and so forth. Again, this number of df can be any positive integer. And for most basic applications, like what we see in our class, if n is the sample size, like the number of people in a poll, then we want to use the t distribution on n-1 degrees of freedom. Actually, the t distribution is used more for small sample sizes. For a poll, n tends to be rather large, and we could probably use a z anyway. But if n is fairly small, then we're really going to want to use the t distribution on n-1 degrees of freedom. So for example, if the sample size is 10, then we want the t distribution on 9 degrees of freedom. Again, if n is 10, if the sample size is 10, then we're talking about the t distribution on 9 degrees of freedom on our basic applications. Remember that student, his real name was William Gossett. Gossett was a researcher for a brewery company, so I guess they cared about just a small number of beers. Who knows, maybe he drank them afterwards. I don't know. But Gossett dealt with small samples at the brewery. Again, as the number of df increases, a t distribution looks more and more like a z distribution. And by the time you get to high numbers of degrees of freedom, like in the hundreds, like for a poll sample size, then for all practical purposes, you can use a z. The t distributions, their tails get thinner and thinner. Remember, the z had very thin tails. The z distribution has very thin tails out here. You have very little probability mass, several standard deviations from the mean. And the standard deviation started off as greater than 1. Okay, for a t distribution, the standard deviation is greater than 1, but as the number of df approaches infinity, as it gets larger and larger, then it approaches 1. The standard dev approaches 1. So the standard deviation decreases. In a way, we're saying that uncertainty decreases, and the standard deviation approaches 1, which is the standard dev for the z distribution. Again, if the number of df is large, like in the hundreds, we often approximate a t distribution with a z, because there's not much of a difference anyway. We can illustrate this using pictures. I used Mathematica to graph these out. So in the figure below, all right, in orange, this orange dashed curve, that's the density curve for a t distribution on 1 degree of freedom. Okay, that's this shorter distribution with thicker tails. It's more squat. The blue dotted curve is the t distribution on 5 degrees of freedom. You can see that its peak is higher up here, and its tails are thinner than the orange tails for the 1 df t distribution. And the idea is that as the number of df, degrees of freedom, gets larger and approaches infinity, the peak gets higher and higher and approaches the peak of the at the z distribution, the peak for the z distribution, and the tails get thinner and thinner. Again, for 1 degree of freedom, the tail here was a bit thick over here and over here. Bear in mind, the t distributions are also symmetric. They're all symmetric about the mean line at 0. And the idea is that we're going from the orange distribution, the t distribution on 1 degree of freedom, to the t distribution on 5 degrees of freedom, up towards this z distribution over here. So it's getting taller near the mean, and it's getting thinner near the tails. And the standard deviation is getting smaller and smaller. We're getting more and more bunched up around the mean line of 0 as we go from the orange curve to the blue to the black. If we're talking about hundreds of degrees of freedom, then the T curve is very, very close to the Z curve, and we may as well use the information for the Z distribution. Like our information from software or tables, we may as well use Z information. All right, we've talked about the Z distribution and the infinitely many T distributions, which had different numbers of degrees of freedom. Next, we're going to talk about the chi-squared distributions, which look a fair bit different. They are a fair bit different. Next time.